This is a picture of a electrical circuit, and there's a light bulb in the electrical circuit, and there's water that's interrupting the circuit in the middle of the circuit. And this little experiment is done to show whether or not the apparatus, in this case water, can conduct electricity or not conduct electricity. And the evidence that it's conducting electricity is the light bulb would be on. The first picture is just in the little container here is just distilled water. Okay, distilled water is pure water, just H2O. Everything's been separated from it by boiling the water away from whatever salts may have been mixed into it. This is a sugar water solution, and this is a salt, just table salt water solution. And what the evidence shows you is that the circuit is complete only in the case of the salt water. That means that this particular solution can conduct electricity and these two can't. And whenever a solution can conduct electricity or carry a charge, then it's called an electrolytic solution. And the solution would be called, or the solute in the water would be called an electrolyte. And when it can't carry a current or a charge, it's called a non-electrolytic solution. So these two would be non-electrolytic, and this would be an electrolytic solution. All right, so this is telling us that there's something different on the molecular scale going on between when salt dissolves in water versus when sugar dissolves in water. Okay, and so again, we're back to this concept of intermolecular forces. Intermolecular forces is what we're talking about right now. And here is what happens when you put salt in water. This explains why the salt is considered an electrolyte, because what happens is the water molecules, are all around the salt crystal, and they approach the salt crystal in such a way that many water molecules will surround, say, the chloride ion, and then when they do, they're going to surround it in such a way that the hydrogen, or the positive end of the water molecule, is near the chloride ion, and there's going to be a strong electrostatic attraction between the positive end of the water and the negative chloride ion. And when enough water molecules surround that chloride ion, then it's going to be enough force to pull the chloride off the crystal. And this is how salts dissolve in water, one ion at a time. And you'll see how the water molecules orient themselves. Once the ions are in solution, they're separated, they're discrete, and the positive end of the water has aligned itself with the negative chloride ion, and the negative end of the water here has aligned itself with the positive end. And so these types of intermolecular forces, these are not bonds, these are very strong intermolecular forces. This is an example of an ion-dipole type of intermolecular force. And the ion-ion is stronger than the individual ion-dipole, but once you have a whole bunch of water molecules, like 6 or 8 water molecules pulling on one ion, it's enough to overcome the attractive force between the positive and negative in the crystal to pull it in solution. Plus, when you go from a nice crystalline structure like this to the ions being mixed up, then there's also a force, an energy force called entropy, that also drives this, because the solution is moving from more order to less order, and that's also a driving force. So it's the additive effect of all of these electrostatic forces on a single ion to pull it off, plus the fact that the solution's getting more, well, we'll just say disorder. So it's going to drive it into solution. All right.